This is a joint work with Emmanuela Orsini.
Nigel Smart.
So this is the outline of the talk. This talk is going to be about multi-party computation. And first, I'm going to introduce a little bit of context on general MPC and on the secret sharing approach that we follow. And then I will explain how you can use Oblivious Transfer in this setting. And then I will talk about our contributions to the area. OK, so what is MPC? Well, we have had many talks today on MPC, so I won't be long on this. Just let me say that in MPC, you have a set of parties, and they wish to compute a target function that is public on some given inputs. To do so, they exchange messages, basically. They engage in a protocol such that the outcome of this protocol is exactly the output of the function that they want to compute. And this protocol, at least, it has one property, which is privacy. So this says that from the transcript of the protocol, you cannot tell anything about the inputs of the honest parties. And this is true even if the corrupted parties deviate from the protocol instructions. So in the 80s, pretty much was said about what you can do or what you cannot do in MPC. If you are considering unbounded adversaries, then you can compute pretty much everything, but you have to assume that at least that strictly less than half of the parties can be corrupted. And this is for the case of semi-honest adversaries. And if you are considering active adversaries, this is adversaries that deviate from the protocol, then strictly less than a third of the parties can be corrupted. On the other hand, you can play with bounded adversaries. And here you base security on computational hard problems. But this typically means that you're going to get less efficient protocols because usually you use public key operations. But this scenario is more realistic. So for instance, you can consider the two-party case, or more generally, you can have all but one of the parties corrupted. So this is the type of security that we consider in this work. We have computational security. OK. So yeah, that was all what I wanted to say about general results. Now let's see how you can actually implement those protocols between many parties, the secret sharing approach that we follow. So the first ingredient is a way to secret share the values in the system, in the set of parties. We use a very simple secret sharing scheme that is additive sharing. And here you break the secret into pieces or shares. The sum of these shares, it gives you the secret. And then each party receives one of these shares. So this scheme is linear, which is good for arithmetic operations. And it supports full corruption threshold. So all but one of the parties can be corrupted. So in this talk, anytime I write x between angles, it means this. It means that the value x has been secret shared in this way. The second ingredient that we need is a way to authenticate these values. This basically ensures that the parties cannot change their mind and open to a different value than the one that was secret shared in the first place. We know of two ways of authenticating the values. The parties can choose to authenticate the shares of the other parties, and they do so by putting tags or marks in each share. So for instance, say that PI has a value X that needs to be authenticated. Then PJ is going to give to PI in somehow a mark MX, and he holds a key that authenticates this value. And this key can be broken in two parts. Well, you can see this key as an affine line, and you can break this key in two parts. The local part relates to the value that is being authenticated, and the global part is common to all the shares. So the global part would be the slope of the function if you think if you think about the key as an affine line. And the other way to authenticate is to authenticate the secret itself. So here you put the MAC on the secret. The only difference with the previous method is that now the MACs and the keys are also additive shared in the system. OK, so this way of authenticating is also linear. And on what security concerns, well, you cannot forge values. So you can't have a MAC that is valid for 2 different values, because that would mean that you also know the key for this MAC. So this happens with a negligible probability on the size of the field where the MAC and the keys are living. OK, so now we can secret share and authenticate values. And we can do this linearly. So we can do additions and multiplication by constant locally. So all is left. All what is left to evaluate circuits or functions is a way to multiply secrets that has been secret shared. And we do so with a standard trick due to Weaver. And it works as follows. So suppose that you have a triple ABC such that the third component of the triple is the product of the first 2 components. So C is equals A times B. And also suppose that this triple has been secret shared and authenticated. Well, if the parties has this triple available, then they can decompose the multiplication gates into broadcast and linear operations, local operations. For privacy, you need the 2 first components of the triple to be randomly distributed. And for correctness, you need this multiplicative relationship in the triple. And then you use the MACs to cope with active adversaries. OK. So this brings us to the preprocessing model. In this model, you split the circuit evaluation in 2 phases. In the online phase is where the actual evaluation of the circuit takes place, using the method that I just explained in the previous slide. And in the offline phase, to generate all these triples. You can see these triples as the correlated randomness that's in some talks this morning was mentioned. So far, we know 2 ways of generating the triples. You can use homomorphic encryption. This is one line of research. Or you can use Oblivious Transfer. And this is what we do in the paper. We use Oblivious Transfer to generate the triples that are needed for the online multiplication. OK. So yeah, now let's see how you can generate these triples using Oblivious Transfer. Well, I guess you all know what Oblivious Transfer is. We know that you can realize Oblivious Transfer from public key crypto, but it's pretty unlikely that can be based in more efficient primitives, in symmetric primitives. As a second best solution, you can realize OT if you assume OT already. So you start with few given OTs, and then you use them to implement a polynomially number of OTs in the security parameter. In 2003, there was a paper that explained how you can do this very efficiently. Actually, you only need to do 3 invocations of a hash function to implement the extension. So Oblivious Transfer is a powerful primitive that can be used to implement many other primitives. And in particular, you can base MPC in this. So this is not new, and it's something that has been around for a while. But the question of can you base practical MPC on OT, it wasn't known until 2012, where there was a paper here in crypto also that they explained how you can do it. So in this slide, I try to give a very brief recap of this paper. And the main observation that the authors made was that if you want to authenticate bits, that's essentially the same to run an OT functionality. So the idea goes as follows. Say that the authenticator, the party that has the key, is going to play the role of the sender. And the other party, the party that has the key that needs to be authenticated, is going to play the role of the receiver. So the sender inputs 2 bit strings. The first bit string is going to be the local key, And the second bit string is going to be the XOR of the local key and the global key. And then as a result, the receiver gets one of those bit strings, which is exactly the MAC on the input that he gave to the OT functionality. OK, so why is this secure? Well, this is secure because they were used, sorry, why is this efficient? This is efficient because they were using ideas from OT extension. So they basically were authenticating many bits at the same time. So all the bits they wanted to be authenticated, the number of bits that were going to be authenticated, it was the same as the size of the bit strings in the OT functionality. But unfortunately, some selective failure attacks arose in the process, and they had to use cat and choose techniques to prevent them. OK, so once they got these authenticated bits, then two-party computation follows. They were able to generate some variants of the triples that they called authenticated OTs and authenticated ANDs to implement the online multiplication. OK, so what we have done, we have taken this paper and we have extended to the multi-party setting. So more concretely, we have used the protocol that authenticates bits, but to authenticate not just towards one party, but to many parties. It's important to note that these bits can be either known to one of the parties or it can be also secret sharing the system. And once you get this way of authenticating, then MPC follows, as we will see later. OK, so how would you use this protocol, the 8-bit protocol, to authenticate many bits towards many parties? So the first thing we thought was we can have one party authenticating the shares of the other part, of a different party. OK, so in this way, you would only need to run n executions of the 8-bit protocol. And remember that this protocol builds on OT, so the less executions you have, the better. But unfortunately, this way is not secure. If two parties collude, then they can just open to the flipped bit. So this attack is not surprising because we are using a protocol that was designed for two parties, but now we are considering at least three. So the third party, it doesn't have the bit that needs to be authenticated, and it doesn't have the MAC on it, but it also doesn't have the keys that authenticate this bit. So it really seems that each party needs to authenticate the shares of all the other parties. But the question is how you do this. OK, so this is how you can do it. Say that P1 wants to authenticate his bit X1. What he's going to do, he's going to first authenticate n-1 random bits, each bit against a different party. And then he's going to XOR his bit X1 with the ith bit and gives this to the ith party. And this party uses this XOR to come up with a valid key that authenticates the bit X1. And then P1 just needs to reuse the MACs that were authenticating the random bits. So in this way, you have pairwise authentications. But we want more. We want global authentications. And you can do this using just local operations. So this is how you do it. Remember the notation. X between brackets means that, in this case, means that P1 has the bit and the MAC on it, and PI has the key. So what P1 is going to do, he's going to add all the MACs that were authenticated towards the different parties, and then he gets a new MAC. And now, in this perspective, the keys that were authenticating the bits, now they are just additive sharings of a key that is secret sharing the system. So there you go, you got global authentications, just with local operations. And with more modifications, the parties can authenticate bits that are not known to anyone. OK, so now the parties can input something and the system can authenticate it. That's fine. But we still need to generate authenticated triples. In fact, we don't generate triples, we generate quadruples because we are using OT, basically. So what's a quadruple? A quadruple are 4 bits, A0, A1, B, and C, such that C is equal to A sub B. If you have quadruples that are additive share and authenticated, then you can use similar techniques as to implement the online multiplications, similar techniques to the one that we know already. OK, so how do you generate these quadruples? We're using exactly the same protocol that authenticates the bits, but now we see it with a different perspective. We don't see it as a way to authenticate bits, but we see it as a protocol that gives shares of the product of bits and some field elements. So with this perspective, it's not difficult to see that you can actually generate sharings, additive sharings of the quadruple. The details are in this and on the right side of the slide, but this is not very important. So the important bit is that you can now generate additive sharings of quadruples. So the next step is to authenticate these quadruples. But now we know how to do it. We know how to authenticate, how the parties can authenticate their shares. So they can input the shares of the quadruple, authenticate them, and then the system can work out an authentication on the secret share quadruple. But we are still not done because there is a subtle problem. So the problem is that each party can choose what they authenticate. So corrupted parties could authenticate a quadruple that is not really multiplicative, and that would mean that we would get incorrect results in the online evaluation. So we need to make sure that they really authenticate multiplicative quadruples. And for that, we use, again, standard techniques to check that one quadruple is correct. Sometimes it's called sacrifice, because you use many quadruples to check that one single quadruple is correct. But now, because we are working with bits, we have to repeat this process many times to achieve real soundness. Or alternatively, you can do it in a batch fashion. So you check many quadruples in one go. And that gives you a better way to do it, in a way. OK, so if you want to see the details, just look at the paper. And so, yeah, to conclude, the message that I want you to take home is that now you can do practical MPC using Oblivious Transfer in the multi-party case. That's it. Thank you.